another situation in mechanics, easy but just cosmetically different. Let me tell you what I'm up to. Let me share this problem with you. So there is this particle which is launched with a velocity 6I cap plus 8j cap plus 20k cap from the ground, let's say, where k cap belongs to gravity. Gravity is in the negative z direction, which is given by minus 10k cap. That means it's launched against gravity. At time t equal to 0, what we want to be able to do is, we want to find the angular velocity of the particle about the point of projection O, 2 seconds later. This is what we want to do, right? Realize that if the vertical direction is gravity, the ground is the xy plane. Right? And velocity component of the particle parallel to the ground. This is the velocity component of the particle parallel to the ground, which is the xy plane. That will remain unaltered because it's perpendicular to the z direction, and therefore gravity will have no influence on the velocity parallel to the xy plane. So 6I cap plus 8j cap, which is the initial velocity parallel to the ground, velocity component parallel to the ground, that's going to remain unaltered, right? However, this vertical velocity, which is 20k cap, is subdued by gravity, which is 10 units opposing this velocity, right? This velocity will get killed in 2 seconds because every second it's losing 10 meters per second. So in 2 seconds, this vertical velocity would have got killed. That means when the vertical velocity gets killed, the particle would have reached its highest position, right? But in 2 seconds, what does not change is the velocity component 6I cap plus 8j cap. That does not change. So for sure, in 2 seconds, the particle would have reached its highest point, and the highest point would have certain coordinates. The highest point would have certain coordinates, would have a certain position vector with respect to O, and once it reaches that point, we want to find the angular velocity of the particle with respect to O. That's what we want to do. But even before I do those mundane calculations, let me quickly brush you past a very simple concept. In a very general sense, don't restrict yourself to imagining that angular velocity is only related to particles moving in a circle. In a very general sense, if a particle is at a point P, whose position vector with respect to the origin is r, and it has a velocity v at a certain instant of time, then its angular velocity about O, is going to, suppose this angle is theta, right? V could have been resolved, this V, whose magnitude is, let's say, V, could have been resolved as V sine theta perpendicular to R, and V cos theta along R. This is the parallel component, and this is the component that produces angular velocity. Omega, again, I assume that mod of R is R. Angular velocity omega would have magnitude then V sine theta divided by this length. Angular velocity about O is going to be given in magnitude by V sine theta divided by R. Now, vectorially, how would you represent? Now that's important. It's important to understand how one could get the angular velocity vectorially. First of all, if this is V sine theta, this is O, then, this is, let's say, the sense of the angular velocity. This is the sense of the angular velocity. But if this is the sense, say a clockwise sense of the angular velocity, there is a direction associated with the angular velocity. These are two different things. The sense of the angular velocity versus direction of the angular velocity, these are different paradigms. The direction is going to be given by the right hand rule. You take your right hand, pledge to get the direction right. Curl your fingers in the sense of omega. This is the sense of omega. Observe your thumb if that's the only thumb you have. The thumb goes into the plane of the board. So in this case, it's going into the plane of the board. The direction of the omega vector, goes into the plane of the board, and that could also have been obtained. Realize that if this is R, this is the direction of R. This is the direction of r. This is the direction of v. This is the direction of v. This is O. R cross v goes into the plane of the board. R cross v goes into the plane of the board. So the direction of omega is the same as direction of r cross v. Direction of omega will be the same as direction of r cross v. Now what I do is, I could have written this as, notice that I could have written this as VR sine theta divided by r squared. VR sine theta divided by r squared. This is what I could have written this as. Vectorially, this would reduce to the following. This would reduce to omega being r cross v divided by r squared. Divided by r squared. Do you relate to this? Because r cross v will give me the direction of omega. R cross v will give me the direction of omega. R cross v goes into the plane of the board. The magnitude of omega would be r into v into sine theta by r squared. R into v into sine theta by r squared, which is the same as this. That means this representation, this vectorial representation of omega will give me the omega vector, will give me the omega vector. R cross v by r squared. So this is what you need to know. So 2 seconds later, I want to know the velocity vector of this particle. I want to know the position vector of this particle, right? And then I'm going to perform a operation r cross v by r squared. That's going to give me the omega of the particle about the origin O. This is what happens, right? Good. So the problem, so this is an important concept. So the objective behind delivering this problem was to make sure that you understand the vector notation associated with omega, right? R cross v by r squared. So if you allow me to remove the clutter from here, let me go ahead and perform the last rites on the problem, right? Let's do that. Remember, I'll just write it here. Omega is r cross v by r squared, right? Okay. So P is the highest point where the particle reaches in this parabolic trajectory, in this projectile motion. The vertical velocity would have become 0. The vertical velocity would have become 0. The velocity vector then, however, 6i cap plus 8j cap would remain unaltered because that's parallel to the horizontal. That's parallel to the ground. That 6i cap plus 8j cap is parallel to the ground. So the velocity vector 2 seconds later is simply going to be 6i cap plus 8j cap. That's going to be the velocity vector, right? What's going to be the x and y coordinates of the particle? Well, in 2 seconds, the displacement in the x direction would have been 12 meters. Displacement in the y direction would have been 16 meters, right? Because the velocity in the x and the y direction will remain 6 meters per second and 8 meters per second. So in 2 seconds, the x and y coordinates of the particle would have become 12 meters and 16 meters. So for sure, x coordinate of the particle 2 seconds later is 12, y coordinate is 16, and the z coordinate would be the maximum height reached by the particle. It's going to be the maximum height reached by the particle. What's the maximum height reached by the particle? That's going to be the z coordinate. That's going to be u initial in the z direction squared divided by 2g. That's going to be the z coordinate of the particle 2 seconds later. That is the maximum height reached by the particle. Why? Because in 2 seconds this velocity would have become 0 and the particle would have reached its highest point, right? So uz squared by 2g means uz is 20 squared divided by 20. That makes it 20 meters. So the z coordinate of the particle is going to be 20 meters. Right? So what's going to be the position vector of the particle 2 seconds later? That's going to be 12i cap plus 16j cap plus 20k cap. So now I have everything at my disposal. The velocity vector of the particle, 6i cap plus 8j cap, and the position vector of the particle. I need to find the omega about the origin. The omega about the origin, like I said, is going to be given by r cross v by r squared. By r squared. R is the magnitude of this position vector. What's the magnitude of this position vector, by the way? The magnitude of this position vector, as you can see, r is going to be root 12 squared plus 16 squared plus 20 squared. So this is 256 plus 144, 400, 20 squared plus 20 squared. So that makes it 20 root 2. That makes it 20 root 2. That's R. That's 20 root 2. And what's R cross V? Let me find R cross V. R cross V, using my determinant notation, I cap, J cap, K cap. And what's R? 12, 16, 20. 12, 16, 20. And what's V? V is 680. This is going to give me R cross V. Let's see what it turns out to be. Let's see what this turns out to be, R cross V. So R cross V, the vector R cross V, which will feature in the numerator of omega, that's going to be I cap into minus 160 plus minus j cap into minus 120 plus k cap into 96 minus 96, 0 obviously. So that makes it minus 160 I cap plus 120 j cap. That's R cross V. That's R cross V. And I know R cross V, so that's like a minus 160 I cap plus 120 j cap divided by R squared. R squared is 800, as you can see. These many radians per second would be the vector representation of the angular velocity of the particle 2 seconds later about the point of projection O. Do you all understand this? So I'm sure, you know, with a lot of problems on projectile motion under your kitty, under your belt, you would have learned a bunch of formulas, bunch of results, this and that and so on and so forth. But then, you know, this one situation I really liked because it just looked different. Was not difficult, just looked different. Welcome to the world of things that look different. Bye-bye, have fun and stay out of trouble.